Hello everybody, this is going to be another thermo video, and in this video I'm going to be going over a heat pump example. So this is going to be similar to the refrigerator example problem in the other video, except this will be a little more different obviously because it's a heat pump. So the question reads, a heat pump with a coefficient of performance of 3.8 provides energy at an average rate of 75,000 kilojoules per hour to maintain a building at 21 degrees Celsius on a day when the outside temperature is 0 degrees Celsius. Electricity costs 8 cents per kilowatt hour. Find A, the actual operating cost and the minimum theoretical operating cost in dollars per day. And B, compare the results of A with the cost of electrical resistance heating. Okay, so to start this problem, I'll write down our givens. So we're given the coefficient of performance is 3.8. We're also given QH in this case. It's the 75,000 kilojoules per hour. Because, so the reason I know that that's QH, so first they're telling you a heat pump provides energy at this rate. So heat pumps, since they provide energy, you know the energy that a heat pump provides is QH. And I'll talk a little bit more about that when I get to the schematic. We also know that the temperature in the building is equal to 21 degrees Celsius, which is also 294.15 Kelvin. We know the temperature outside is 0 degrees Celsius, 273.15. And we know that the cost is 8 cents per kilowatt hour. Okay, so with that, let's go ahead and get our schematic drawn. So we have a T hot for our hot reservoir. We have our pump. And we have a T cold for the cold reservoir. Okay, so what's the purpose of a heat pump? Well, a heat pump is going to provide heat to our hot reservoir. So I've mentioned this example before, but let's treat our hot reservoir as a house. So say in the wintertime, you want your pump to provide heat to your house, obviously, to warm it down. And we're going to treat the cold reservoir as the outside, right? So the cold outside. So the pump takes in heat from the outside and provides more heat into the interior of the home. And in order to accomplish that, you need to input some work. All right? So that's exactly how ours is going to look in this case. So we call this heat leaving the pump, QH, and heat entering the pump, we call it QL. And then the work provided into the pump is W in. All right, so from here we can actually try to solve this problem. So let's write that off to the side here. Okay, so let's start off with something that they give us. So we're trying to find the overall cost. So the actual cost and the minimum theoretical cost. So let's start by finding the actual cost. So we know the coefficient of performance is 3.8. And we know that the equation for the coefficient of performance for a heat pump is again the desired output over the work in. And for a heat pump, our desired output is QH. because this is the heat that's going to be warming our house in our example. So therefore QH over input work we know is 3.8, and we know the value of QH. So we should be able to solve for WN now. And we can go ahead and do so. I'm just going to keep the units as kilojoules per hour. I'm not going to convert it quite yet. So that means WN is 19,736.842 kilojoules per hour. So that means that this value is the actual power input to obtain QH value with the given coefficient of performance. Okay, so with this work input, now we can find the actual cost. So to find that, we know the work input is 19,736.842 kilojoules per hour. Okay, and just doing some dimensional analysis here, we know that 1 hour is equal to 3,600 seconds. So now I'm just going to convert that, the work input, that is. So if I do that, if I do the math, 19,736.842 divided by 3,600, we get a work input, or power input I should say, of 5.482456, and it's going to be in kilowatts now. So that's kilowatts because, you know, joules divided by seconds is just watts, but you still have the kilo in front, so just kilowatts. So with that, so now that it's 5.482456 kilowatts, we have to convert that to dollars per day. So we bring in our conversion factor, which is, we know that 1 kilowatt hour is equal to 8 cents, right? So that means this kilowatt would cancel with this kilowatt. So we're still left with an hour in the denominator. So since we want to get this to dollars per day, we have to convert the hours to days. So we know that 24 hours is 1 day. So now this hour should cancel with these hours. And now we're left with dollars per day here. And if you evaluate the numbers out, you'd get that the actual cost is $10.53 per day. All right. So we're not done with part A quite yet. We still have the minimum theoretical cost. So for the minimum theoretical cost, the key to this is we're assuming the heat pump is reversible. All right. Okay, so assuming the heat pump is reversible, we know that the equation for the coefficient of performance, I should say the maximum coefficient of performance, is TH divided by TH minus TC. So this is true for a heat pump. And if I put in our values, we know TH is 294.15. That's the temperature of the hot reservoir. And in our case, the hot reservoir is our building that we want to keep warm. And then TC is the cold reservoir, which is the exterior. So the cold outside, which is 0 degrees Celsius, which is 273.15 degrees Kelvin. So if we evaluate that, we get COP max of approximately 14. So we know that, again, the coefficient of performance equation for a heat pump is the QH over WN. So that means 14 equals QH over WN. And QH remains the same as 75,000. Because that doesn't change. So if we go ahead and solve for the work input for that case, we get 57.143 kilojoules per hour. And then doing the dimensional analysis for that is the same as what we did in the last step. So we have 5357.143 kilojoules per hour. Convert that to kilowatts. We need to get rid of the hours and replace them with seconds. So the hours cancel. So kilojoules over second, we know is kilowatts. And if we evaluate that, we get a power input 1.48809 kilowatts. Okay. So now with that, again, in our other dimensional analysis, 1.48809 kilowatts. We have the factor, the conversion factor, I should say. So we know 1 kilowatt hour is 8 cents. And this is running for 24 hours because 24 hours are 1 day. So kilowatts cancel, hours cancel. So we're left with dollars per day. And if we evaluate that, we get that minimum theoretical cost is $2.86 per day. All right, so then that's it for part A. So just to recap, the first part of part A, the actual is $10.53 per day, and the minimum theoretical is $2.86 per day. Okay, so now going to part B, we want to find the cost of electrical resistance heating. So you might be wondering, well, how do you find that? So in order to find the cost of the electrical resistance heating, we need essentially to find out what QH is. I mean, we're given QH, but QH is the heat that is leaving the pump, which is being used to heat the home. So that's why we have to look at QH to get that the cost per day. So we know that QH is 75,000 kilojoules per hour. Again, I'm just going to do this in my calculator, but this is the same. I'm going to convert QH from kilojoules per hour to kilowatts. So similar to this guy here, this factor, it's the same one we've been using. I'm going to do the same thing. So 75,000 kilojoules per hour times 1 hour over 3,600 seconds. We get 20.833 kilowatts. All right. And now from here, again, we bring in our conversion factor. Same one as before. So again, it's 8 cents per kilowatt hour. Kilowatts cancel. You have to get rid of hours. 24 hours in 1 day. Your hours cancel. So now you're left with electrical resistance cost. If you evaluate that, you get that it is approximately $40 per day. All right, so that's kind of how you walk through this specific example. It was mostly dimensional analysis. Yeah, once you really understand the cycle and what's going on, it's really just number crunching after that. All right, so I hope you guys enjoyed.